Welcome back to the channel. So we just finished up building the Elmer's number 33 steam horizontal mill engine. If you haven't seen that, you can check out the playlist for it. And now it's time to start a new engine. So pretty excited about this one. I have never built a Stirling engine before. So I've got the plans here. We're going to build the Jerry Howell Miser low temp Stirling engine. So to start with, we're going to take a look at the plans, not in great detail, but just sort of go through them, get an idea of what we're getting into. And then we'll look at some material that I've got gathered up and then go from there. So this engine is a Stirling engine, which we'll go over a little better detail when we get more into it of how it works. But the basic idea is there's a plate here at the bottom and a plate at the top, and then there's a disc in here in the middle. And if you heat or cool this disc on the bottom, it changes the temperature, obviously hotter or colder, which changes the pressure inside of here. So going from a high pressure to a low pressure, it will move this piston up and down, which is connected to the crankshaft, to this, they call it a displacer rod here, to this displacer ring. And the change in the pressure from the temperature and the heating and the cooling will make this disc move up and down, which will make this move and the flywheel and the piston up and down. Hopefully as we go along a little bit better, it'll make more sense. So looking at the plans, there's a main column here, a bearing holder, and I think they call this the main frame here. Just to get an idea of what we're getting into. There's a couple more columns here. This is the crosshead guide. So this will have a crosshead similar to like what a steam engine would have, and this will also, you can adjust this and set the timing. So there's a certain timing between when the disc goes up and down and the timing to the piston, kind of like the valve on a steam engine. We've got a balance disc here. We've got the piston, which is going to be graphite. So the plans say that it's extremely important that the piston is something that can resist temperature, so you wouldn't want to make this out of like aluminum or brass. We got a connecting rod here made out of some aluminum. We have two plates that make the bottom and the top of the displacer. This is 6.400 inches in diameter, and then there's 12 holes drilled around it that sandwiches the top and the bottom. This is the displacer ring, which they recommend making out of PVC or some type of plastic. It says do not use metal or any other kind of heat conducting material for this ring. So you need to isolate the bottom displacer plate from the top displacer plate for temperature. So there needs to be an insulator in between those. This is our displacer disc, which is foam. And the flywheel, which is aluminum. And the crank and some connecting rod. So this just gives you an idea of how the engine goes together. This is the displacer plate at the bottom and the top, and then the plexiglass in between it, and then the foam. And we got a main column here, and then a cylinder and a crosshead guide and the flywheel. So, and then there's construction notes. So when you purchase these plans, and I'll put a link down in the description of where you can purchase these from the Jerry Howell website. They also sell you can optionally buy some of the materials to make this engine. So I did purchase from them the plexiglass ring. You could source this, but for the price, I figured it was better, and it's the right diameter. We'll have to turn it down on the ends here and get it good and flat, but for the price, I just went ahead and got that from them. And then they also have a foam disc that we'll make our displacer out of. This should be the correct thickness, because there's a certain thickness that you need this to be. It can't be too tall or too short to fit in here, because it'll take up too much space. Then they also sell a little package here that comes with the bearings. So this will run on ball bearings, because you need to have as little or as close to zero friction as you can for this engine to run. It runs off of the temperature differential, so it's not going to make a lot of power. So if you've got any kind of friction or binding, it's not going to want to run. So this is a piece of graphite that we'll use for the piston. And then there's some Delrin here that goes in, I think, some of the bushings. I'm not sure exactly what all this gets made into. And then there's two tiny bearings here. These will get pressed into the end of the top brass piece here. So you can purchase the plans, and you can purchase these materials from the website when you buy the plans. So the first thing with any project, I always go through my scrap bin, go through the plans, and then see what kind of material I'm going to need. Try to use up as much scrap as I can. Occasionally have to purchase some material, so I did have to purchase some material for this. But I've got two 1/8" discs here that will turn into the top and bottom plates. And I've got a 1" square piece here that's too long right now, but we'll turn this into this middle column here. Then I did have some scrap piece here that'll be the main frame that's 1/4" thick that I've got rough cut out. And I did have a piece of scrap 3/8 aluminum here that will turn into a flywheel. Then I did have to purchase a couple of pieces of cast iron. I decided to gonna do the crosshead guide and this cylinder out of cast iron and this balance disc. So there's enough on here to make the crosshead guide out of this one, and then the cylinder and the balance disc out of this piece. So these are 1.5" cast iron. And then I did purchase a piece of brass that will be this top bearing holder here. And I did buy this material cut to the rough, a little bit oversized, but cut to close to what the length is going to be that we're going to need in the end. And then that's all the material that I have. Everything else is smaller pieces that we'll come up with out of the scrap bin when we get to that point. So I think to start with, I want to start with these displacer plates. So I'm going to take these plates here, and I'm going to put some layout fluid on them and go ahead and get the center marked out. And then this gets drilled and reamed for 1/4 inch. And then we'll rough cut these out on the bandsaw, and then we'll get these mounted up on an arbor and get them in the lathe, and then turn them to the 6.4 OD. And then we'll get them laid out and get it set up to drill these 12 holes. And these are clearanced for a 080 screw. And I need to decide whether I'm going to use countersunk screws or counterbore. I haven't decided there yet. I'll see what kind of screws I've got, and then we'll figure out what we need to do there. But the first thing we'll do is get these laid out, get this hole drilled and reamed, and then get these plates turned down to size. Okay, so I got the two discs made for the top and bottom of the displacer. So bandsawed those out and then mounted them on an arbor and then turned them down in the lathe to the correct dimension. This line here is where our bolt circle is, and we'll drill those holes once I get the bolts and I know what kind of size countersink that I need to use. And then while I was at it, I went ahead and cut out the piece for the flywheel. Did the same thing, marked it out, cut it out on the bandsaw, mounted it on an arbor, and then turned it down to size on the lathe. Then I went ahead and put these chamfers on here that it calls for. And then this is a 1/4 inch in the middle because I've got a 1/4 inch arbor but this does get reamed out to a larger size at a later date, but we can do that once we can mount it in the chuck on the lathe and then make that larger later. So that's going to do it for the machining, but I'm going to go over, I don't think I did a good job of explaining how this engine actually works, so I've made some diagrams here. I'm going to go over again exactly how this engine works. So to start with, here at the top, we've got this foam piece, which is called the displacer, is at the very top of this cylinder. And this is a sealed system. And this chamber is open here to the piston, so air can travel from here to this side of the piston, and the piston is sealed into the cylinder. And then this rod here is also sealed, so this entire system here is airtight. So to start with, we have the displacer at the very top, and then this piston is at the very bottom of each stroke. So in this case, you can do this with heat or cold, but I'm going to go over this explanation with using heat. So heat from the bottom is going to warm this bottom plate, which is this plate that we cut out here. This is isolated from the top plate, so that's why we have to use Delrin here and plexiglass so that it's insulated from the top plate, so the top plate stays cool, which is the blue, and then we apply the heat at the bottom, which is the red. So once this heats up inside of here, the air in the displacer cylinder heats up, then the pressure inside of this system increases, and that's because of the ideal gas law. So PV, pressure and volume, equals nRT. So the volume is not going to change. So as the temperature in here increases, the pressure is going to increase. So as the pressure in here increases, it causes this graphite piston to be pushed up. So once this pressure in here increases, it pushes this piston up. That in turn is connected to the crank here to the displacer rod. So as this piston goes up, it's going to turn the crankshaft. And there is a lead between the displacer and the piston, and they're 90 degrees. So the crank pin on the displacer is 90 degrees to the crank pin for the piston. So as this piston goes up, then it's going to push the displacer down in the cylinder. So as the displacer goes down, it pushes the hot air that's here at the bottom. So this is not a completely tight seal. There's a little bit of an air gap between this displacer and the ring. So as this displacer goes down, it pushes the hot air up to the top plate where it cools. So you can see the red is the hot air, the blue is the cold plate, and then the green in between is where this hot air, where they're mixing together, and then the hot air is cooling. So once that air cools back down, it decreases the pressure in this system because, again, it's sealed. So as the temperature goes down, because the volume doesn't change, the pressure is going to go down. So this decreases the pressure and then pulls the piston back down. Once the pressure goes down, it pulls the piston back down. So as this piston goes back down, it moves the displacer back to the top, and then that forces the cool air that was up here in the top back down to the warm plate at the bottom. So as the displacer goes up, the cool air goes back to the bottom, and then that starts the cycle over again. That cool air will heat, and then once it heats, the pressure goes up, pushes the piston back up. So there are 2 power impulses per revolution, which is an interesting idea. And then the cycle just starts again, and then it just keeps going back and forth, heating and cooling the air. So hopefully that makes a little more sense. of how this engine is going to work. And it's not a real powerful engine. I know there have been some engines back in the day, they did make like fans and some smaller stuff that would run off of this, but never was able to really scale this up to make any kind of serious power out of it. So that's going to do it for this episode. Come back next time and we'll probably going to start machining on the flywheel and get the spokes and everything machined out on that. Thanks for watching.